Good evening, ladies and gentlemen. Thank you for turning out on quite a cold evening. I want to talk to you. See if I've got the right gadget here. I want to talk to you tonight about. Well, the title I've called is, as you see, is Oil on Troubled Waters. I want to talk to you about Britain's industrial legacy. And I have to say, it's impossible to do this subject justice in a short period of time. So I'm going to give you some examples and then pose at the end of the lecture some questions. I want to focus on groundwater because it's part of the water environment that we don't normally see until we pump it up and it emerges in the taps. Or occasionally, we do see it, occasionally in very prolonged wet periods, you see groundwater emerging through the floor of your house or in the street or whatever. But normally, it's out of sight, and obviously the phrase is out of sight, out of mind. I should say, though, also that the recent debates on fracking in various parts of the UK have raised the possibility or have raised the image, if you like, of groundwater contamination in the public mind and perhaps in the minds of our politicians as well. Before getting into the talk, though, I just want to share with you a little snippet of film which was about the reception given to one of Britain's politicians, Lord Brown, when he tried to talk about fracking and groundwater contamination. So, see if this will run.
To the US Secretary of Energy, there are no known cases of groundwater contamination as a direct result of the hydraulic fracking process.
It's great, isn't it? A really English reception when he says that there's no possibility of any fracking giving rise to any groundwater contamination. Terribly polite series of escalating throat clearings. Okay, so I want to talk about the types of groundwater problems that we know about already and how they've come about. But I also want to reflect on whether those are real and genuine problems, or whether they're the result of some kind of hysterical response to contaminants that might be present naturally from substances that aren't perhaps in any case harmful. Or perhaps they're only present at what I might call homeopathic concentrations. I hope I'm not going to upset anybody there who's a fan of homeopathy. But I mean there by the kind of concentrations that we talk about might be individual molecules in billions of litres of water, for example. So we'll come back to that in a minute. This is probably not a scene that most of us see. It's an area where there's been problems with oil, and that's one of the examples that I am going to look at. There are some major problems associated. There are some major problems associated with groundwater that are of health concerns. The big picture there's gone slightly wrong, but there is a very distressing story about groundwater containing high levels of arsenic in Bangladesh. And many of you probably know where Bangladesh is. It's the mouth of the rivers here coming down from the Himalayas, the Ganges and the Brahmaputra. Bangladesh isn't normally an area that we'd associate with water shortages. It's very low-lying and it floods a lot. But actually there is a shortage of good quality drinking water, and many of the population are reliant on what are called out there tube wells, just basically wells, tubes into the ground, and they puncture those fine sediments. So this area that's if you like, the delta of those big rivers is made up of very fine layers of sediment, and those sediments over thousands, if not millions of years, have washed down from the Himalayas. You can just see the snow in the top of this satellite image. Now, those wells, there's probably 35 million people dependent on those, particularly in the south of the country. And some of them have very high levels of arsenic. The picture here has gone slightly wrong, but the levels of the red levels there, the areas close to the sea, close to the mangrove swamps along the coast here, have very high levels of arsenic in them. And of course, how that actually came about, those levels of arsenic, is very much disputed. Some people have said it's still disputed in scientific terms. Some people have talked about it being the result of fluctuating groundwater levels associated with pumping of these wells, because as soon as you pump the water, you allow oxygen into the sediments in the ground, and people say that helps to release the arsenic into the drinking water. Other people say, no, it's not that, it's to do with what happened millions of years ago when these sediments were first covered up by other sediments before there were any people around. So it's not clear. But a couple of things are not disputed. One is that high levels of arsenic ingestion in drinking water are associated with very serious diseases, and I'll show you these very unpleasant pictures. They're associated with chronic damage to human health, so these horrible skin lesions on people's feet and hands and elsewhere, and they're also associated with cancer and things such as diabetes and nerve damage and cardiovascular diseases and so on. Arsenic is cumulative, so it builds up in your body. And Bangladeshi people then in these areas that have high levels of arsenic are faced with what I would call a wicked dilemma. You can choose to die of arsenic poisoning over a long period of time by drinking the water from these wells, or you can perhaps die of diarrhea by drinking surface water that's got bacterial contamination in it. That's a pretty salutary situation. Of course, in the UK, we are not dealing with that level of contamination, and we shouldn't forget that. But that's the first problem. It's not disputed that arsenic, in this case, leads to health problems. The second thing that's interesting is, and problematic is that responsibilities for this are very, very difficult to establish. Years ago, research was undertaken in this area of Bangladesh by the British Geological Survey. And they were doing an analysis, actually, of water resources for an irrigation project. But as a side effect of that, they identified water sources being available, and that report, it was a 1992 report, which was intended to be done as a charitable donation, I think it was part of Britain's aid programme, informed the administrators out there who used the data from it to install a lot more wells. Now, the British Geological Survey had not analysed the water for arsenic. It wasn't part of the arrangement. But in 2004, the British Geological Survey were sued by some very, very angry Bangladeshi residents, alleging that the British Geological Survey had been negligent and should have told them about the arsenic. Now, in fact, the case was dismissed in 2004. It was in a British court, actually. It was dismissed on the basis that the British Geological Survey didn't have any responsibility for telling residents that there was arsenic in the drinking water, and they had no duty of care, as it were, to Bangladeshi residents. Now, you might or might not think that's just, but it's a good illustration, I think, of some of the complexities around establishing legal responsibilities for groundwater. The other picture that I have up here just really flags up the fact that we haven't always been so averse to using arsenic. Of course, I don't know whether anybody here has ever used this kind of arsenic complexion soap. I haven't, but evidently at one point it was regarded as desirable. Okay, so attitudes to this kind of substance have varied as well. Okay, now Britain was the home of probably the first, industrial revolution, and that's the previous one, not the one that today is creating new digital industries, but the industrial revolution that focused on more material things. British cities, as we know in the past, were dirty, where life was often, as other people have described it, nasty, brutish and short, and pollution was an inevitable partner to the growth of industries and houses and transport systems. I'm sure many of you here today will know, and those listening online as well, will be familiar with the Great Stink in the Thames. It was occurred in the later 19th century because of the complete lack of sanitation in the city. So all sorts of organic and inorganic wastes, and you have to think slaughterhouses, tanneries, cloth manufacture, sewerage and so on, percolated directly into the ground and into little sewers that fed directly into the Thames. The river became so polluted with sewage that it was almost biologically dead, which is the situation that's almost identical to the situation in Bangladesh that we saw earlier. The main river in Dhaka today in Bangladesh is a kind of oily, green-black flow in which you see a few organisms trying to eke out an existence, a very sad existence. Ganges dolphins, for example, looking very ill indeed. The point about the Great Stink in the Thames in the later 19th century is that it caused Parliament, first of all, to close down because they couldn't stand the smell, and then it motivated politicians to take action. Now, that was largely the result of organic pollution. Industrial pollution is probably a bit less well understood in both a conceptual sense and in a scientific sense. Some of the best descriptions that we have of 19th century chemical processes come from novelists like Dickens. And as a boy, he worked, and perhaps many of you are aware of this anyway, but as a boy he worked in somewhere called Warren's Blacking Factory, which greatly, of course, influenced his attitudes to poor Londoners at the time. He was very young, and his family were financially distressed, and he picked up the issues of poverty there and included them in the stories later. Personally think he was less good to women. They get a notably poor deal in most of his stories, I think. But blacking is the polish that's used on boots. And the 11-year-old Dickens was putting that into bottles and pasting labels onto them. Now, blacking was a mixture of waxes and something called lamp black, or carbon black, which is actually a soot. It's a substance like soot. It's made from charring all kinds of organic materials like bones and all sorts of stuff. And the thing is, it contains all sorts of trace elements. Things like carboxylic, quinonic, lactonic and phenolic complexes. These are volatile things that evaporate easily and they are toxic. I'm going to come back to some of those substances later, but of course they are carcinogenic. They're certainly carcinogenic to animals. The position is not quite so clear for humans, but it's perhaps fortunate that Dickens's nasty and brutish employment at the factory was relatively brief, otherwise we probably wouldn't have experienced his novels later, his storytelling later. But with any of these things, with any of these kind of industrial activities, there are spillages. They may be deliberate, they might be accidental, and the fluid seeps into the ground. So you only have to think what happens at the end of the day, or even quite recently what used to happen at the end of the day in factories where people were painting things. They just pour the surplus paint out of the window at the end of the day because it was too much trouble to go and deal with it appropriately, or perhaps there wasn't any way of dealing with it appropriately. So there are spillages into the ground. Sometimes, as I said, there are big deliberate spillages. One of the things that happened well into my lifetime was that some of you will probably remember the big town gas cylinders that you used to see around the town. Yeah, am I? Big storage of gas cylinders. Well, they fell out of use largely, and when they were dismantled, the workmen frequently used to just sort of stove in the bottom of the tank. And in the bottom of those tanks was huge amounts of tarry substance, a volatile organic compound that was just left to seep into the ground as being the out of sight, out of mind. And still today, we sometimes find that when people are doing excavations in the middle of town, when they're digging up water mains or whatever, you find the remains of these areas of tar in the ground, sort of seeping around. Now, in many cases, I'm not going to go through the detail of the chemistry here, but unlike organic mixtures such as sewage that will actually break down or recycle very quickly, there's a cartoon. I'm going to move on very quickly, but a lot of organic stuff breaks down very quickly, but not everything. And certainly inorganic materials that come from some of the major industrial processes that went on in British cities, like this one's in steel manufacturing in Sheffield. These people are grinding, in this case it's a foundry. There's another picture here, I think, of them sharpening stuff and using various compounds in order to treat the metal. And this stuff spilled into the ground. So, and it's much more persistent. So in some cases it hangs round in groundwater for a very long time. Now, the smelting, things like paint production as well, oil refining, all the branches of the chemical industry, many other manufacturing industries that lie outside cities, they also generate contamination, and it feeds into the groundwater. It's complex and expensive to clean up. Now, if we just listen to this chap for a second.
The Environment Agency will carry out tests on the land at the Dale Farm Traveller site near Basildon this week after fears that it could be contaminated. Last autumn, Basildon Council dug up part of the site to prevent travellers living there illegally. The area was previously used as a scrapyard.
Okay, so another example of contamination. In this case, the implication is it's come from the use as a scrapyard, and presumably in the scrapyard, fluids like brake fluid and so on from cars were being released into the ground. Now, complex and expensive to clean up. Here's a local example where there has been quite a successful clean-up, and some of you in the audience I know very well have actually walked this area not so long ago. The Olympic Park in East London was contaminated. This sort of thing had been going on, but in addition to that, there were all sorts of inadvertent spillages. The two maps here are on the left. You can see here's the Olympic Park here in 2012. But if you look at the street map beforehand, you can see railway sidings, industrial areas, and all sorts of other things in that space. So it's an area that we know was contaminated. It was successfully cleaned up. I won't, again, go through the details now of how that was done. But actually, if any of you watched Danny Boyle's Olympic opening ceremony, there was actually specific reference to industrial contamination and the clean-up explanation that followed. The clean-up, in this case, for the Olympic Park, was clean-up of soil, so something like 2 million cubic metres of soil, but also 200,000 cubic metres of groundwater, 80 Olympic-sized swimming pools. Now, the other reason for me just making this point is that I'm going to talk about both contaminated sediment and the groundwater that's in it, and that's because they're inextricably linked together. What happens is that the contamination is usually in the sediment, and it gets into the groundwater under certain conditions, which we'll explore in a minute. The other problem with trying to monitor and report on contaminated groundwater is that it moves around. So actually you're safer reporting the sediment that's in the ground, because that tends not to move around. Okay, so, right. Now, here's an example of a spill. It's a leaking oil tank or something like that. I want to just explain for a minute how water moves through the ground. And I've got a little video here which just explains that, a couple of minutes of video. So let's just watch that for a minute. Now what you've got here is a tank divided into two, and you can see that water's been put into the right-hand side, so there's a high level of water on the right-hand side and a low level on the left. And it's moving through the tank from one side to the other. And there's some dye that's been put into it so we can track what's going on. Now, you can see if you look carefully at this that the material that's in there is actually quite variable. It's sand, but you can see it moves quickly in some places, slower in others. But the thing that I want to emphasise here is that the water, even in a situation like this, follows quite a complex, curved pathway. Okay, now that's quite an important thing to remember, because the water, what's happening in this case is water is being squeezed through a narrow gap, and each particle of water interferes with ones around it. So it's effectively being squeezed by, in that case, a layer underneath the tank that the water can't get into. Now, some of you will be familiar with some of the terminology. Perhaps I can just, might just run that again, actually. See if we can run that again. Yeah. So what we've got here is the sand represents an aquifer, a water bearing and a water transmitting rock. The water moves through it as if it's in a sponge. It moves because there's a difference in the height of the water level on one side on the other, and that's what we can call the piezometric surface. This is not something really to drop into your pub conversation, but it's the water table in simple language. So the water table is higher in one place than another, on the right than on the left, and it's pushing the water through the gap, and it's following this curved pathway. Now that, as I say, those curves are features of the movement of groundwater everywhere. It's not specific to this. This is a more or less uniform material with, at the bottom, a layer through which the water can't pass, and that's called an aquiclude. So it's impermeable, the water can't pass through it. So in nature, that would be a layer of clay, for example. Now forgive me if you're very familiar with all of this. But what I want to emphasise is that real situations are much more complex than that. Sometimes different aquifers are stacked up like a sandwich, so you'd have layers of bread making up the aquifer and some meat, which is the impermeable layer, the aquiclude. And in reality, of course, an aquifer, as around London, for example, can be tilted or it can be broken, fractured, and it might be topped up with different amounts of rainfall in one place from another, particularly if we're talking about a very big scale. So it's quite complex, even in that very simple, what we looked at there, which was essentially a two-dimensional experiment. Okay. Now, if we add to this a third dimension, not just a slice, but a third dimension, things get even more complex. This is a computer model showing water moving in 3 dimensions. So you can see that it's an image. We've got the shaded areas representing the ground surface, and where we've got those vertical lines, those are wells. So somebody's taking water out of those wells, pumping it away. And you can see the coloured lines there are zones of contamination. So on the bottom left of the image, there's some contaminated water. It's a spill of something, let's say, and it's essentially being drawn towards the wells in those curved lines. Now here's another one, another example, similar sort of thing. We're looking down here on a ground surface. We've got some houses and there's a slug of water that's contaminated, the blue here. And here we see water, contaminated water, seeping out in a very complex way. In fact, if you look carefully, you can see that it's coming out at 2 levels. The well in the middle, this one here, is actually lower than the other 2, and that's sucking this sort of thread, this pathway down to it, whereas on the top, on another level, we've got another sort of slug of contaminated water going over the top. So it's a very complex system. That's why I've written here, groundwater moves in mysterious ways. The truth of the matter is, actually, even though we can do that kind of thing with computer models, in order to understand what's really going on in groundwater, you have to measure it for real in the field. There's no other way of establishing what's going on. So I want to talk to you about an experiment that I was involved in a few years ago now, in the late 1990s, when I was doing some research for a company called Gulf Oil. I don't know if any of you remember Gulf Oil? Yeah. We'll come back to what happened to them in a minute. But this was their oil terminal in West Bromwich. Now, an oil terminal is not the same as a refinery. This is an area where, a place where oil is stored while it's waiting to be picked up by tankers and taken to service stations or supermarkets or whatever. And you can see there the cylinders that it's stored in, and here, beg your pardon, over here you can see, just about see on this really grainy image, the tankers coming in to pick up certain types of fuel. In those cases it would have been leaded or unleaded or diesel or whatever it might be. Now, this site was built in the 1960s, and the oil used to be delivered to it. You can just about see along the top here, there's some railway sidings, and those of you that have got railway, the men amongst you perhaps who've had model railways might remember those little trucks that had cylinders on them. Do you remember oil cylinders? And they would come by train. So trains used to pull in here with tanks full of oil and unload it, and then it would be stored in these cylinders that you see here. So different kinds of cylinders had different kinds of fuel in them. Okay, now, the oil actually, you can imagine some of the problems here of transporting oil from a tank on a train to get it into one of these storage vessels, and it got spilled. Of course it got spilled. Later on, actually, things improved a little bit, and the way it's done today, which always amazes me, is that oil is delivered by pipeline all the way from Milford Haven in West Wales, and it comes along, different kinds of fuel comes along through pipelines in kind of chunks. So you'll get miles and miles of oil of one sort, or fuel of one sort. Then you get a slug of water, and then they put another kind of oil in, comes along behind, and magically in the pipes they don't get muddled up, which I find extraordinary. But anyway, that's how it's done these days. But again, it's the same principle. When it gets to the pipeline comes in here somewhere, and then it's piped and stored in some of these tanks here. Now, this particular place, West Bromwich, some of you may know it. It's in Birmingham, and the map here shows you the grey area there is Birmingham. It is pretty grey, actually, for real, but here's Birmingham, and the area that I'm talking about is down here, near Oldbury. Do we have anybody from... Don't have anybody with Birmingham connections? Okay, so it's in the north of Birmingham, and it's the River Tame that I'm interested in. That's in blue on the map here, this river here. Goes around there and then up there. Actually, it's a truly horrible river. It's a river which is unbelievably contaminated. I'll come back to why in a minute. But this is the area, this is the centre of the world industrial revolution. So, what does the river look like? Well, I put this photograph in. I was quite amused by it, actually, because it's put in as an example of a river that was bad and has been improved. This is apparently the bad one, and this is the improved version. You can make your own judgment on that. I think I liked it better before, actually. And I put along the bottom my experience of what is taken out of rivers like this, which does include handguns. Anyway, it's a pretty contaminated river. The area is, the geology, again, don't worry too much about the exact nature of the geology, but the catchment is underlain by sedimentary rocks that can transmit water. And the red one there, the one in red, is the Sherwood Sandstone, which is a major aquifer, and a lot of drinking water comes out of it. So remember our area of interest is over here. Here's this big aquifer, and the grey areas here, this is the coal measures. So these are rocks with coal in them, and that's why we have the Industrial Revolution, or one of the reasons we have the Industrial Revolution in this area. So what was being made in Birmingham is things like metal-related industries, cars, the manufacture of brass, jewellery, gunsmiths, and so on. Now, in the 1990s, some work was done on water quality in this river, and it was classified as something called River Ecology Class 5. Now, rivers are classed, or were then classed on a scale of 1 to 5, where 5 was basically horrible. 1 was really nice, you know, pure as a mountain stream, that kind of thing. 5 was really disgusting. And so bad was the situation that the plans for doing something about it included the fact that it was likely to go on to be class 5, even if they attempted to clean it up. The map that you see on at the moment here, and we should be looking at this pie over here, the grey sector here, this shows pollution incidents. How many were there in that area in, I think it was 1993 actually, that. And that's the proportion of them that were related to oil pollution. So there were other kinds of complaints about it, spills and leaks as well, so there were chemicals in it and sewage, and actually apparently some agricultural pollution even close to the centre of the city. And solvents of various sorts, again, those used in the metal industries and in things like dry cleaning, which again we'll come back to in a minute. So when I was looking at this river, I actually was given a research grant by Gulf Oil to come and have a look at this site, and I found not only oil everywhere, but this kind of thing, where you can see here coming out into the river. Well, you can see the oil here in the river, on the surface of the river, but there's also these ochreous or iron compounds seeping out of the riverbank into the water and covering the bed of the stream and so on. It's a pretty unpleasant river. I did once see a kind of wheezy-looking kingfisher going down it, but almost no other signs of life. And more excitingly, one day there was a burning car in it, and the water was actually on fire as well. But anyway, it's a pretty nasty place. Now, that map that we've saw indicates why there are problems. That there were rivers around along one side, the River Tame, as we've said, and there were canals on the other side, and a lot of concrete. Now, just touch on this one for a minute, this slide. This is the result of some much more recent research done in 2001 by somebody called Ellis, and it refers to something called volatile organic compounds. Now, I didn't actually do research on these kind of compounds, but these are all artificially manufactured compounds. You can see they have horrific names. A couple that we'll come back to later are TCE, which is on the left, and PCE, which is the third one along. TCE on the left is a solvent that's frequently used in the metal industry for cleaning up engine parts and things, and PCE is dry cleaning fluid. You can find that PCE referred to sometimes on the little labels in your clothes. Perk is its shorthand name. Okay, and in the River Tame there are high concentrations of these things, and these things are definitely, most of them, seriously carcinogenic. They have some numbers on there that refer to how the drinking water limits. And if you look at the black column here, it says what proportion of the samples are over the limit for drinking water. And you see, for example, the TCE, trichloroethane, something like 70% of the samples collected were over the drinking water limit. So they're toxic, basically. Okay, as I say, we won't go through all of those, but there are lots of things in this river. Some of it is definitely coming out of this site. Perhaps not the dry cleaning fluids, but some of the other things were coming out of this site. Now, the company knew about this, so what they did was, along the side of the river here, they built a gravel-filled trench. It's called a French drain. It's basically just a trench with gravel in it and a pipe. And then at the end of it, down here, the idea was that the groundwater from this site would be caught in this drain, and then they put a big pump in here, pumped it up, put it into this tank here, where they could try and skim off the oil that was coming out with it at the very least. I think I have a picture of that. Yeah, there we are. There's me standing by this tank, fiddling around. That's my water sampler there that ran by itself. The river is down over there somewhere, and this is the canal tunnel, and here's the tank, and you can see in here there's oil floating around on the top of the water. Basically, if you put it in a big tank like this, the oil comes up to the top, and then you can try and sort of mop it up. And then when they'd done that, the rest of the water just overflowed back into the river. If you look at the, I've got a satellite image of this site in 1999 where everything had been cleared away. So here's the river here, going under the canal actually. There's another canal. And if you look carefully, you can just see the tank still there. Can you see that there? There's the tank. And you can see these spaces where all these storage areas were in the car park and so on here. That's the situation that we were looking at. What I also knew, though, was that this terminal, when it was built in the 1960s, had been built on top of about 10 metres of industrial refuse. And that was industrial refuse from the Industrial Revolution, from the middle part of the 18th century onwards. I've got here an aerial photograph taken in 1945, and you can see, here's the same site, there's the river, the canals and so on. You can see the remains of bits and pieces here, but all of this stuff in here is rubbish from the Industrial Revolution. So it's rubbish from the metal smelting industry, from a wagon works that was there, and all sorts of other stuff as well, goodness knows what. Things from the chemical industry and so on. Now, why Gulf Oil asked me to have a look at this was because the Environment Agency, actually then I think it wasn't the Environment Agency, it was their predecessor, but they were leaning on them to do something about this site because it was polluting the river, clearly was polluting the river. So the Gulf Oil asked me to come and have a look at what was going on and try and work out what they could do about it, what they could reasonably do about it. So we put monitors and so on all over the site. You can see here we sampled water, it's me sampling the river water there on the left, and research assistant of mine on the right there sampling some of the groundwater. So you can see the train tracks there. This thing here is called a bailer, and if you look, there's our little hole, and she's just dropped that down. If you look carefully at it, you can see that at the bottom it's yellowish, and that's water, and floating on the top of it is about 1 metre of oil. So underneath this site, we've got a kind of floating lens of oil that's been spilled over the years, and some of the oil is actually dissolving into the water and making it this yellow colour. In fact, the amount of oil came and went, which made us think that they were spilling stuff even then, although, of course, they denied it. I should say, too, that it's actually very difficult to do research on a site like this because there's a risk of explosions. And you can't sort of use batteries to run equipment and pumps and things because everything has to be what's called intrinsically safe. I'm sure there are people in the audience who know about intrinsically safe working, but it was pretty problematic. The working environment, as you can see, isn't particularly pleasant. I have to say that I actually had an unfortunate drenching once because one New Year's Day when I was taking water samples on my own in this river, I slipped and fell in, and I had quite a struggle to get out, but that's largely because I was holding my water samples because I thought, I'm not going to let go of these, and I had a heck of a job to try and just climb out of a sort of snow-covered bank. But anyway, I won't go through all the analyses we did. We did quite a lot of analyses, and we were assisted by a student from Coventry University as well, who did some analysis of the types of oil that were there. But if you look at this kind of image, one of the things that's quite startling here is if you look at these bottles, it's actually almost a simulation here, but the bottles of water, if you took a bottle of water out of that French drain, which was under the ground and had water coming through it, if you then exposed it to the air, you can see what's happening here. Black particles of iron and manganese are precipitating out. They're appearing in the water and then dropping out to the bottom of the bottle. So the chemistry of this water is really volatile. It's changing all the time as it's exposed to air. And of course, it's going into the river, and that's why there's nothing much living in there. Now, we wanted to try and find out a bit more detail about what was going on. And so we did all sorts of monitoring. We must have measured, well, we did measure thousands of samples of water, the chemistry of thousands of samples of water. But one of the things I'll just show you is what happened to the water levels during the course of this year. Now, think back to the tank that I showed you earlier. Water flows from a high point to a low point in terms of the water levels. And what we've got here is the contours of that water surface. So you can see over here, this is early in 1997. The water's at 19 metres along there, so this is a high point up here, 18 metres and dropping down as you approach the river to 17 metres. Okay, so the water's moving from up here to down here, which is what you'd expect by a river. However, as time went on during the period, it was quite wet that year, and what we observed was the water level rising very quickly after rainfall. So we're measuring rainfall, we're measuring flows, we're measuring water levels. This is April of 1997. Sorry, let's go back a minute. This is April of 1997, and you can see here there's a kind of a hill, if you like, a bulge of water coming in at the top of the site here. It's 25 metres, so a sudden surge of water coming in. Close to up here there was a canal, if you remember the image. It's a sort of seeping down across the site in this kind of curious way. If we go forward to June, you can see it's gone even further across the site, and it's got more complex as well, and it's sort of pushing down into and through the site into the river. And what this actually reflects is actually probably billions of litres of water coming through this site, bringing with it oil that's kicking around in the site, and also other materials that are in the contamination, in this 10 metres of contaminated rubbish from the Industrial Revolution. Now, in fact, the site managers started to get really excited and anxious because the Environment Agency got very cross. And what they did was, the site managers, they attempted to build another kind of structure to trap some of this water and to treat it, to stop it overwhelming everything and coming through the French drain and into the river and so on. And they built a sort of trap with a pit with plates in, and the oil is supposed to settle on these plates and come out. Again, I won't go through the details of the science, but so unpleasant was this water that all sorts of stuff, algae and stuff, was growing on these plates. It was like something out of a science fiction movie. So every time you lifted up the cover on this thing, there was this kind of organic mass inside growing. And they then had to treat it with herbicide to try and stop it growing, because it's stopping the equipment working. And in fact, they seriously underestimated the volume of water, because before we did this, they didn't know about this big bulge in the water coming through. They began running up a monthly bill of thousands of pounds just on the chemical treatment of some of this. The other thing we discovered was in the middle of the site here, somewhere here, there was an area of highly saline water, very salty water, just appearing in the middle of the site. And I haven't got a diagram of that, but these legacies of the Industrial Revolution, the other things that were in there included arsenic, chromium, manganese, and so on, ammonium, nitrates, phosphates, and so on. Some of them are the chemical breakdown products of the oil, but an awful lot of them are not. And every time it rained, a pulse of them, all of this stuff, was going into the river. Now, the point is, in this catchment, in the catchment of this particular river, the Tame, there are hundreds, if not thousands, of similar sites. And the same would be true of parts of London as well. In this particular case, we know quite a lot about what was on the site from maps. And these are not very good reproductions, I'm afraid, but up here, this is a map from 1887, and there is the legacy of a coal mine and various works. Down here in the 1920s, there was actually a wagon work, so doing metal bashing and some foundry work. And here it is in 1955, derelict, but with tipping going on, in fact, of industrial refuse from elsewhere in Birmingham. So it's pretty difficult to manage. We've got thousands of litres of water pouring through the site. We've got a historical legacy of contaminants and very difficult hydrological circumstances. Now, I will just tell you one other thing. Towards the end of the research programme, we had quite a lot of fun trying to measure how rapidly water was moving through the site. And what you have to do there is you have to measure something called the hydraulic conductivity. If you imagine a sponge, it's how big the channels are through the sponge, or how big the channels are through the sand that we saw in the tank there. And normally what you would do is you'd have a borehole, hole in the ground, and you'd pump water out of it. And then you'd observe how far around this point the water was being pulled down, the level was being pulled down. And that you can work out from that how fast the material will conduct water. Our problem was that we couldn't pump any water out of these boreholes because it was so contaminated, it would have cost us hundreds of thousands of pounds to pay for it to be treated and taken away. So we had to think of another method of doing it, and we actually did it by connecting up the fire hoses to the top of these boreholes and pumping water into them to raise the level, pumping clean water into them to raise the level, and then observing how quickly it dropped in the borehole. And I can tell you that how wet everybody got doing that. If you can imagine the size of a fire hose on an oil terminal is very, very big, huge volumes of water. Anyway, what we discovered, in fact, of doing that was that not only was there contaminated material under the site, but there were kind of voids and holes and channels in it as well, where the water could literally pour through in huge quantities. Now, the research finished rather abruptly because Gulf Oil went bust, and they were bought by Shell. And Gulf Oil were very concerned about what we'd found, and they put an embargo on publication. That embargo, there was a 10-year embargo. It's lapsed now, so it could be published, and I can talk about it now, but we couldn't at the time. By 2014, despite the contamination, the site had been sold. And here you can see the same river. Here's the Tame, the canal, and you can see that it's been sold, and it's got warehousing on it. It's bright and shiny warehousing. If you look really carefully, you can just see at the top of the site that tank is still there, actually, the little rectangular separation tank. But it's been sold. It's been sold for another industrial use. Now, and some attempt at clean-up was made. Now, before we draw out some conclusions from this example, I just want to touch on a couple of other examples of contamination of different sorts. Here's an example of something called trichloroethane, which we did talk about before. Almost everybody in this room will have used this if you've ever used Tipex. Have you ever sniffed Tipex? It's exciting stuff. All sorts of things follow if you sniff Tipex, but TCE is one of the ingredients of that, but it's also used in paint remover and adhesives and so on. And here we can see a map showing a factory somewhere down here, and there's been some kind of spillage or leakage, and there's a plume of this stuff moving towards this river in the ground. Now, the thing about this is that this stuff is heavier than water. So whereas my oil was floating on top of the water, in this case, what we've got here, you can see the aquiclude, the impermeable layer here, and the blue line is the water table. And where you've got the red, you can see that, and the darker colours, you can see that it's settling under the water, underneath the water, in the hollows, in the bottom, underneath. So that's an example of a substance that's a dense fluid. There's been a leak, but it leaks and goes under the water. It's not dissolved in it, and some elements will dissolve in it. But that's what happens with that one, TCE. And there's another one here which is somewhat similar. This is the dry cleaning fluid example. And the same, more or less the same thing is true in this example. So over here we've got something that's leaking. Over here we've got a well. We've got something leaking over here, and it's drawing, in this case, two lines of very high concentrations of dry cleaning fluid towards the well, which is a public water supply. Okay. Now, in this particular case, this one, some of this will actually break down. It will actually decay. The point about them is these things are irritants. They're associated with all sorts of health complaints, liver and kidney complaints in the case of the TCE one. And both of these are almost certainly, for example, in groundwater under every city, including London. There are what we have is areas then of contamination where we don't know what's present. That's the truth of the matter. You see here, regular or unleaded. We've actually got all sorts of contamination in our water which we don't know about, and some which we do know about. Now, I want to ask a few questions about this situation and how we manage it. We clearly already know that there are lots of problems in modelling just where the water is going, because it moves in such complex pathways. And wherever we look, we find volatile organic compounds in the water. This is just an example of the sorts of things that have been reported as acute problems. Just a few, just selected. There are, as I say, thousands of other problematic sites as well. In 1987, there was first, very late on, actually in the 90s, not 1987, in the 90s, was the first example of where anybody had ever tried to study this at the level of a city. It seems extraordinary that it wasn't done before, but it wasn't. And what was found in that instance was that under Birmingham, that area in Birmingham, for example, 80% of the wells were contaminated with that TCE material, 80% of them. Yeah, I've got a diagram here. This was work by Rivet, development of it. Everywhere you see a large circle was where it's in contamination levels well over the health limit. And in fact, the health limit for this particular substance is 10 micrograms per litre. So for this one on the left. So you can see there it's all over the place. That's the Sherwood Sandstone that we talked about before, actually. But everywhere here where the rocks are exposed, it's there. It's seeped into the ground. Now, as I said before, that aquifer is a major source of water, and taking those substances out of the water is going to be very expensive. We know that substances are widespread in contaminated land across Britain's city. Here's an example of two sites in Glasgow and just some metals that are found in those sites here. There's a comparison here with Turin and Uppsala. But if you look here, the levels of lead, this is in parks. This is sediment in parks that somehow got there and created contamination. The mercury levels appear very low, but the toxic levels for mercury are also very low. So actually it's significant. That's significant too. But you can see Glasgow is in a worse situation for most of these metals than Turin or Uppsala, for example. This is the map for lead in London. I don't know where you live. Most of you are in London. But the redder it is, the more lead there is. And some of this is leakages from industrial sites. Some of it is fallout from vehicles. But where there's a hot spot, the dark colours, it's likely to be some industrial legacy. Okay, now, so we find, wherever we look, we find potentially a kind of lethal cocktail of these chemicals, perhaps. And the other thing we note about this is that our laboratory capabilities, though, they are improving all the time. So one of the things that's going on here is, this looks terrible, but actually, one of the reasons we're finding more and more substances is that our laboratory capability is getting better all the time, so we're able to detect them, whereas 10 years ago, we may not have been able to detect them. Okay, so that's the second issue. The second question I have is whether this is actually quite such a problem as might be implied by some of these maps. Now, clearly, there is a third issue about whether this water will get into drinking water supplies. The literature indicates that there are, as I say, thousands of wells in the UK affected. We know a lot more about some of these chemicals in water that we actually drink than we ever did before. So things like hormones and endocrine disruptors and so on, which are industrial products, pharmaceuticals leaking into groundwater. We know a lot more about that, and that too is problematic. We're finding them, they're in tiny concentrations, but we are able now to find them. So not only are we using them more, but we're able to identify them more in the water. It's just...
Developers say the controversial clean-up of a former agrochemical factory site near Cambridge is now complete. The land at Hawkston was contaminated during the 1940s, and there were hundreds of complaints when it was decided to dig up the soil, treat it, and then return it to the ground. Some claimed fumes from the site made them ill, but developers Harrow Estate say the 20-month clean-up has been successful, and they've submitted plans for the first phase of over 200 homes for the site.
Okay, now a couple of reasons for just showing that very brief clip. First of all, it's pharmaceuticals. That's a new industrial product, or what's been found there was a new industrial product. The other point about it is it was cleaned up for housing. Okay, now that requires a very high level of cleanup. In the UK, it would be true to say that we have good levels of protection on our water supplies, and as the Department of Environment, Food and Rural Affairs said in 2009, there's no evidence for widespread impacts of contaminated land on human health, although you can see there's a caveat there. The potential for human health impacts hasn't been dismissed. Okay, so that's because everything is so uncertain, and part of that uncertainty is in the legislation too. This is how we legislate to deal with this at the moment. This is the Contaminated Land regime, the Environmental Protection Act 1990. And if you look at the wording, I won't again read it all out, but you'll see that there's lots of reference to significant harm and significant possibilities of significant harm and significant pollution and so on. So there's lots of uncertainty about how the definition of whether something is polluted or not, how that is done, but there's also uncertainty about how you sort it out. So you see that it says at the end there, remediation must be to a standard that the land is suitable for its current use. So what we're saying is, even if you clean it up, it depends what you want to use it for. We're not cleaning it up forever, we're cleaning it up for what we think we might want to use it for. So if we want to use it again for industrial uses, as in Gulf oil, we'll have a lower standard required. It will have to be done again if we ever want to use it for housing. So, in the UK then, we can't say we've got a health problem with contaminated groundwater. We can't say that we haven't got a health problem either. And we're discovering more about those health problems, and our ability to actually monitor them in our groundwater is developing all the time. I want to give the last word to the Royal Commission on Environmental Protection in 1996. They said it wasn't aware of any study that provided firm evidence of adverse effects of contaminated land on health. I think the thing I want to leave you with is, first of all, to say that the Royal Commission on Environmental Protection was actually wound up not so long ago. But I want you to leave you with the thought that whether you're convinced that we actually know enough about this. I leave that with you. Thank you.